He's going to tell us about the partition function of Abelian Chern-Simons theories on handlebodies. Over to you, Massimo.
Thank you very much. Thank you for the invitation. Sorry for being late a few days. So the time difference played a trick on me too, in spite of knowing it intellectually, but then you forget it when it matters. Today I would like to talk about Chern-Simons theories on handlebodies. And so let me first say that this is work, this seminar is based on a paper written with my former student Cedric Yu, who now is a postdoc at the University of Kentucky in Lexington, and is published here in JHAP. Well, let me start by noticing by giving you a little bit an abstract of what's to come. I'll introduce Chern-Simons theories, and I will just mention that these theories acquire a dependence on metric data from boundary conditions, though Chern-Simons theories on manifolds without boundaries are topological. And then that means that when one computes partition functions of Chern-Simons theories on open manifolds, these are not just numbers, are not topological invariants, but are wave functions. And of course, the question is, which wave functions are they? Well, we know an answer for Abelian Chern-Simons. We know a basis of wave functions that have some interesting properties. And we also know an implicit basis of partition functions for Abelian and non-Abelian Chern-Simons. So we know how to relate implicitly a given partition function to a given wave function obtained by canonical quantization of Chern-Simons. What is not known is how to relate the various bases of wave functions. So there is one that has certain analyticity properties and is given by some explicit theta functions, etc. There is another basis that instead which is implicit. We don't know actually what the wave function is, but we know what is the relation between the wave function and the partition function, and the point is to relate the two. So to relate a given partition function to a very explicit linear combination of wave functions in a given basis that I will explain and describe explicitly in a few minutes. So to do that, we need, so to relate this basis of wave functions, we need a few ingredients. The first one is a radial quantization of Chern-Simons, and in particular, we'll have to discover that radial quantization of Chern-Simons also implements a projection over gauge invariant wave functions, and then we'll have to give, in a sense, an initial condition for the radial evolution. So once we do that, we'll be able to have a very explicit formula that relates partition functions of Chern-Simons with or without Wilson loops to a given wave function obtained by canonical quantization of Chern-Simons. I will start by explaining what is the explicit form of the partition function for Chern-Simons without Wilson loops, and then I will introduce Wilson loops, and I will show how one can recover even subtle properties of the Wilson loops, like the framing anomaly. I will finish my talk by explaining what we have been able to do so far regarding partition functions of non-Abelian Chern-Simons on handlebodies. In this case, the handlebody that we understand is pretty simple. It's a torus handlebody. But even in this case, when we compute the partition function of non-Abelian Chern-Simons on a solid torus, we discover an interesting identity that we have been able to prove only by brute force and only in a special case, but we suspect it's more general than that. So without further ado, let me start by recalling a few facts and notations about Chern-Simons. So first of all, the Abelian Chern-Simons theory has an action, and the bulk Lagrangian of this action is written in terms of an object that is is one of a top form, but is not, because the Abelian connection that appears in this formula, of course, is not gauge invariant, but changes by a gradient. So if you look at this, at the action that I call I here, well, you may think that it's topological, and indeed it is topological on manifolds without boundaries, but a dependence on the metric structure and on the complex structure of the boundary is introduced because when you have a manifold M with some boundary that I call sigma, you need to add a boundary term to the action. And the boundary term is the one that I call here IB, and that I choose here, introduces a dependence on the complex structure simply because you need a complex structure, in this case, to define what you call the holomorphic and anti-holomorphic components of the gauge field. So, of course, what I wrote here is not the only boundary term that I can write, but it's the one that I will use, and it's the one that gives a partition function written in terms of the holomorphic component of the gauge field, and therefore depends on the complex structure. So here, I mean, Chern-Simons is an interesting theory because it seems almost trivial in the sense that all the dependence on extra data on the complex structure or the metric comes from the boundary, but the boundary is also related to the bulk. And so there are some subtle connections between the two and subtle constraints. So that's what makes maybe this theory interesting, even though it's rather simple and it's, after all, an Abelian gauge theory. Okay, so
Massimo, one question.
Yes.
So usually one talks about chiral WZW model on the boundary, right, of the Chern-Simons theory.
Yes.
So that one should think of another type of boundary term that one could write down.
Now, this boundary condition that I wrote here gives rise to, if you didn't have any topology in the bulk, right? If you computed, for instance, the partition function on the sphere, on the solid sphere, on the ball, will give rise to the partition function of a WZW, of a chiral WZW. When you have some structure in the bulk, when you can have actual, when you can have moduli, when you can have harmonic fields, then your chiral WZW is coupled to a harmonic field, some source, and that's what creates a wave function which depends on, say, the bulk data. So yes, the answer is that the boundary term shows that your bulk theory can be written in terms of a chiral WZW, but a chiral WZW that is coupled to some source, and the interesting part of the source is the harmonic part of the gauge connection, of the boundary value of the gauge connection. And then there is some correction, there is some prefactor that depends on the moduli, right? And that cannot be fixed simply by knowing that your theory is a chiral WZW. So there is, you have a chiral WZW plus something else, and this something else comes because your theory also knows about the bulk. And indeed, we can start to see this by looking at the functional integral. So the functional integral that I want to compute first is the one that I write here. So no Wilson loop insertion, just the bulk action and the boundary. I fix the anti-holomorphic component of the gauge field on the boundary. The holomorphic component, of course, cannot be fixed. You have to integrate over it. And my manifold, my three-dimensional manifold, is a handlebody. So in particular, it's in a sense what you can get by filling a Riemann surface, or by knowing that in the Riemann surface you can choose half of the homology cycles and fill in the in the three-dimensional manifold. Actually, when you cut along those homology cycles, you will get a disk, right? A contractible space. So now, when you have the functional integral, actually, you can think of how you can compute it. Well, you can start with with a related problem. You have a boundary for your manifold, which is two-dimensional. So you have you can also define a wave function, a wave functional, where the argument is the anti-holomorphic component of the gauge field. And to define a Hilbert space, you need a gauge invariant scalar product. This gauge invariant scalar product is related to the partition function, because actually the same boundary term that appeared in the partition function also appears in the definition of the scalar product. In particular, you see that both here and here you have the level k. Okay, so now once you have a scalar product with this exponent, right? You, by imposing that the scalar product is gauge invariant, you also discover the explicit form of the gauge transformation of the action, if you want, of the.
I have a question.
Yes.
So in this scalar product between phi and psi, in the exponent you have minus k by pi ib. That ib depends on both a and a bar, or just?
Oh, it depends on both a and a bar. Yes, because
so if you integrate just a bar, then it will have an a dependence left.
Well, this integral is the integral that I wrote for the scalar product is an integral over a bar and its complex conjugate. So
it's both over a and a bar.
Yes, exactly. So where a and a bar are really complex conjugate to each other.
Okay.
So you see, and let me see here, did I write the IB? Yes, the IB is this one. Now, and here, when I write the scalar product, really, this is what I call the A bar. AZ is A bar complex conjugate. Now, if you impose that the scalar product is gauge invariant over here, then you get the gauge transformation of psi, and the gauge transformation tells you that well, the gauge transformed wave vector is psi computed on the gauge transformed connection times this prefactor. You can obtain this prefactor in many ways, for instance, by integrating the Gauss law, or simply by requiring that the scalar product is gauge invariant. You will get the same result.
I have another question.
Yes.
So if you have exponential minus k by pi a times a bar, and if you integrate over the a, then you're left with a delta function over the a bar, right?
No, because these are not independent fields. Remember, I say that a bar and a bar star called a are really complex conjugates. So you are here. I'm not integrating over some path in the complexification of a. I'm integrating over I could have integrated over a real a. I could have called a1 and a2, right, instead of az and az bar. So
yeah,
in this integral, a bar and a are not independent.
In the sense that a1 and a2 are independent, I could guess that.
Yeah, so you have a1 square plus a2 square. You have a Gaussian integral.
Yeah. So
but an integral is not a delta.
So it's some sort of a holomorphic integral, is it?
No. No, this is not a, sorry. This is, no, this is important. This is not a holomorphic integral. This is an integral. If you have a single complex variable z, that will be the integral in d to z of a function of z times z star.
Okay,
So
maybe
this is not a holomorphic integral for the gauge invariant for the scalar product.
No, what I'm concerned is that if you have, in general, when you have A1 and A2 independent, you can rephrase it. And real. You can make a transformation to A and A bar variables and treat them as independent, usually. That's what is usually done.
Well, when you have the exponential of minus x squared times the exponential of minus y squared, and x and y are real, you integrate in x and y, right, on the real axis, you will get, well, a Gaussian integral. There is no independence and no divergence, right?
No,
I repeat, A in this integral, in the gauge invariant scalar product, I integrate over A bar and A bar complex conjugate. They are not independent. I repeat for the fourth time, they are not independent. Okay, so now actually these wave functions are even known explicitly because we know an explicit basis of wave functions that was found long ago by Boss and Nair. They satisfy the Gauss law, and they are actually for a compact U1, they are a finite number of independent wave functions that are labeled by an integer, well, an element of zk, so just k integers to the power g, where g is the genus. So you have a finite number of wave functions, and that are written in terms of theta functions. And here, the boundary value of the anti-holomorphic component of the gauge function, A bar, appears in this way. A bar can be written in terms of an exact part, the d bar of some function chi, and then some harmonic component. Omega I is a basis of the Abelian differentials on the Riemann surface, and U are just complex numbers. So here, instead of A bar, you see that this A bar has been split into the harmonic part and the exact part, chi. And this this entire wave function has a prefactor that depends on the period matrix, omega. And the function f is what appears actually in when you compute the determinant of the Laplacian on the Riemann surface, minus the zero modes, and without the zero modes, you divide by the imaginary part of the determinant of the period matrix, and what you would get is not the absolute value square of a holomorphic function. It is the absolute value square of a holomorphic function times an extra object, which is actually the Queen-Line anomaly in a sense. I mean, it's a term that was discovered in the mid to late 80s by various authors. And at one loop, actually, when you compute this expression on the torus, well, this S actually can be reabsorbed into F, because it's the sum of a holomorphic part plus an anti-holomorphic one, but in general, it cannot. Okay, so this is all well known, but the question is, it's very simple. Which linear combination of these basis vectors is the partition function? We have a partition function defined in terms of a functional integral. We have a basis of wave functions that we obtain by doing a canonical quantization of Chern-Simons and by imposing Gauss's law. And well, so Z should be some linear combination of its sides. Which one is actually the question that we want to answer?
Massimo, sorry.
Yes.
So for genus G, how many dimension? I mean, this should match with the dimension of the Hilbert space. I just missed the counting of these basis vectors.
So it's here this. So zk has k element, right? And then you have genus G, so you have k times G
Okay.
independent wave function.
Uh-huh. And that's exactly the number of conformal blocks on this genus
yes.
for abelian. I see.
So
and the partition function is one particular vector, right? One particular vector.
It's one particular vector. In fact, you may ask one question that you may ask is where are the other and what do they mean? And actually, this question was actually answered implicitly by Witten in 89 when and here is a drawing of the conclusion. So if you take a handlebody and you draw Wilson loops inside the handlebody, well, you have some that are drawn along contractible cycles and then they contract to zero, and some that instead go along cycles that are also non-contractible in the three-dimensional handlebody. For abelian theories, actually, you can get all the wave functions, all the independent wave functions in your Hilbert space by choosing all the possible independent Wilson loops in this construction. The Wilson loops are, in a sense, the world history of mesons and of charge K, and that's sufficient when you deal with an abelian theory. Witten showed that for non-abelian Chern-Simons, you also need more complicated objects that you can think of physically as the world history of baryons, and they are loops where you introduce vertices, where lines can split and join. So you have also Y-shaped object, etc. So instead of just loops, you may have, say, objects where you have, say, one line and then another line that splits off and is joined here by a vertex that you can write when the theory is non-abelian. For the abelian theory, instead, just by considering Wilson loops inside the handlebody, you can construct all the wave functions of your basis.
Massimo, sorry, one question. So for torus, at least for non-abelian case also, the Wilson line basis should suffice, right? That's what.
Yes, Wilson line should suffice. So there you can go through the various charges of your. So you can go from charge 0, which is of course the partition function without Wilson loop, charge 1, 2, 3 through k, and then.
No, I mean even for non-abelian case, even for non-abelian case, because the number of integrable representations match with the conformal group. That's what I had in mind.
Yeah, I mean, Witten also used this baryon construction. I mean, the construction where you introduce vertices. Now, I don't know if this is just a different parameterization that you can obtain by considering different representations of the Wilson loop. That's a good question. I mean, there could be some redundancy, right?
Yeah, because I would imagine there are lots and lots of Wilson loops and their configurations. So I was at first thought I was thinking that it spans the Hilbert space.
Yeah, for what I recall, they needed also this other object, but now it could be that the construction is not unique. The one thing that, again, we should ask is when we say that we're sufficient needed to what? Well, we already know the answer, to generate a complete set of wave functions on the Riemann surface by the state operator correspondence. So a Wilson loop creates a state. I mean, if you take if you cut a little solid tube around the Wilson loop, right, that will generate a wave function, and you blow it up, and that generates a state. So the state operator correspondence tells you that inserting Wilson loops in partition functions, you should get everything, all the Hilbert space that you also obtain by canonical quantization. But it's not clear how to relate the wave function that you construct with the state operator correspondence and the explicit wave function that you have in the Bosnier basis, because the Bosnier basis is far from being generic. It is holomorphic in the gauge connection in A bar, but it's also holomorphic in the complex structure. So it's a very special basis. Again, our question is essentially how to relate the partition function with Wilson loop that we know is sufficient to span all the Hilbert space with this other basis, which is the Bosnier basis. And the first element in this dictionary is to find what is the partition function without Wilson loops. So to do that, again, we use the state operator correspondence. And and we use it in this way. We take the handlebody and we do a foliation as a Riemann surface times an interval. And then we construct our partition function as a time evolution in this radial time, in the radial time of radial quantization, from some initial state psi 0 to a final state. So we write this functional integral. This functional integral, we write it as a kernel in between an appropriate initial state, evolution in this radial time, and the final state, which is a coherent state. The evolution Hamiltonian, well, the radial evolution is determined by some Hamiltonian. And we actually know H explicitly. And if I wasn't totally clear, maybe let me go back because this is an important point. And maybe I should try to find when you do a radial evolution, actually, so you start with some initial surface, you evolve for any amount of time radially, you will get actually a wave function that is gauge invariant independently of the initial wave function. So radial evolution equals projection over gauge invariance. And we'll see this thing at work, but very soon. Before that, though, let me notice that when I said that my manifold is obtained by foliating a Riemann surface, I skipped on a very important fact that, of course, this foliation has to degenerate somewhere because M is a handlebody. And that is actually quite important, right? Because it will tell us basically what must be the initial state. So when you describe a handlebody with a foliation, of course, this cannot be true everywhere. At the origin, at radius r equal to 0, the manifold is regular, but the foliation is singular. So you can think of the case of actually any handlebody can be written by gluing together some parts that are essentially cylinders. And you see that if I foliate this three-dimensional cylinder in terms of two-dimensional cylinders, at the origin, of course, my description, my coordinate system, my foliation breaks down. So there must be something that tells me that here at the origin, this space is regular, though the foliation is not. So what I have depicted here is the handle of a handlebody, and I have shown here a contractible cycle, which is generated by some vector. Now, there is a convenient way of describing the vectors that generate contractible cycles, and that's in terms of some other quantity, some quadratic differentials that are called Strebel differentials. So treble differentials are quadratic differentials that are meromorphic, closed. Well, they are meromorphic, therefore they are closed, and whose horizontal trajectories cover almost all the Riemann surface. So you have a Riemann surface. On this Riemann surface, you can define these differentials. These differentials have the key property, besides being meromorphic and closed, is that their horizontal trajectories are defined almost everywhere. So they cover all the Riemann surface except possibly a set of dimension 0. Now, a horizontal trajectory is a trajectory in the coordinate z of the Riemann surface of the leaf of my foliation, right? For which the quadratic differential computed on that particular trajectory, so h dz dt square, is real and positive. So that's the definition of a horizontal trajectory. And of course, the vertical is when instead this object is negative. Now, why I'm so interested in this differential? Well, it's because actually this h is a quadratic differential. This means that actually, in terms of it, I can define a metric for the Riemann surface. This metric is flat almost everywhere except at the singularities of my differential. The metric is given here, it's square root of h bar. I can also define a two-valued vector field. Two-valued because I have to take the square root of the Streber differential. In terms of this vector field, the trajectory is simply given by the derivative of the coordinate equal to the vector times some real function. Now, in order to define this trajectory, this real function will have to vanish at the points where the Streber differential, at some points at least, for instance, the points where the Streber differential has a singularity and maybe also some other cut. But that is not bad because when you define a trajectory, right, and you define a velocity or a tangent vector, this tangent vector may vanish somewhere on the trajectory. And still the trajectory, the integral curve is well defined. So the point is that you have this quadratic differential that is defined on the Riemann surface, and it may have some zeros at some point. This object, the vector, in terms of this differential, you can define a vector field. The vector field may have branch cuts because it's defined in terms of square roots of this object h, but actually they cancel in the ratio when you take the complex conjugate of the vector field divided by the vector field. As it turns out, this is the quantity that will enter in our calculation. So we, you may say, why don't you start by defining a vector field on the Riemann surface? Well, as you know, a vector field on the Riemann surface has to have zeros, right, determined by the Riemann-Roch theorem. And these vectors and their integral curves are not really good objects that define homology cycles. The Streber differential instead defines homology cycles. It defines homology cycles because homology cycles can be defined by, in terms of what we call horizontal trajectories. So in terms of quantities that contain the tangent vector square, right? You can also use this differential to define a vector field. This vector field may seem problematic because it may have branch cuts, but it's not, because actually we use it all to define trajectories. And to define trajectory, you don't need the vector field per se, but you can always multiply it by some fudge function f. Concretely, also, the quantity that we will need is not the vector field per se, but is the ratio. Okay.
Sorry, Massimo, what does it mean to take ratios of two vector fields?
Or the components of the vector field in this local coordinate.
Oh, okay. And what are these points where these differentials are singular?
these points are essentially the points. So you can construct a Riemann surface by joining cylinders and then pans. Right? So you can take spheres with 3 holes. When you join the pans, at some point you will have points where you have a union of 3 pans, right? So you have 3 tubes that join together. At that point, your Strebel differential is 0, actually.
I see.
So that is where this vector v will become singular.
I see. But that point meaning, you know, now, this y shape is clear at a degeneration place where you take it all the way to, you know, r equal to 0, right? That's where it should degenerate to y. But when it is away from that, it's a full Riemann surface. There is like proper pair of pans. So the point is 1 point near there. Is that the point?
Let me see. So maybe I can stop sharing for a moment and drawing a diagram. Let me see if I can share from here a whiteboard. Okay. So if I can, of course, have 3 pans and join them, say, attach them to a sphere with 3 holes, right? And construct a Riemann surface by repeating this construction over and over, right? Now, on the other hand, I can even shrink this sphere, right? And then at this point, right, the point over here, I will have that my homology curves have to do something strange, right? Because you have 2 homology curves that join and then become 1. In a sense, join and split. At this joining and splitting point, you need some kind of singularity for your differential, some kind of 0.
On the back also, right? On the back side also?
Oh, yes. On the back, you have also the same thing, right? Because you have some joining and splitting.
Okay. Thank you.
You can move around, but not avoid. Okay. So now let me share again the screen. So, and where is the? Sorry, I have to find now my talk, which I may have. Okay. Here, here's 1, and annoyed long key. This is it, right? Yep. So back we are, and let's see where we were. Homologous. Okay, so we were here, right? We say that the branch cuts cancel in the ratio.
Sorry, you haven't shared the screen, I think.
And did I share? No. So why didn't? Let me see if now it works. Keynote now, and now we are almost there. And now we are there. Yeah. So, okay. So these horizontal trajectories can be chosen to be homologous to the homology cycle of the Riemann surface, the Foliation manifold. So we have, of course, we have many Strebel differentials. We can choose Strebel differentials in which these curves generated by the vector v, right, or better by any real function f times v, are homologous to the contractible cycles on the handlebody. In the Riemann surface, you have some homology cycles that actually become contractible in the bulk, right? So let's choose the horizontal trajectories to be precisely those cycles, the ones that shrink to zero in the bulk of the three-dimensional handlebody. Well, then you need to, then your initial state, the state from which you obtained the final one by radial quantization, must be special, because we know that the handlebody is non-singular at the origin, even if the foliation degenerates. So it means that actually, for when you compute a gauge field along this trajectory and along the vector that generates the trajectory, this gauge field must have zero. This component of the gauge field must be zero on the initial vector. So if you take maybe the simplest case is the torus, if you say that the direction, the angular direction phi is the contractible direction, A of phi at the origin should be zero, right? Not just homologous to zero. If you want your integral, your functional integral to be well defined, right, at the origin, the angular component of the gauge field must be equal to zero. Now, in radial quantization, you have some initial state, and if you want the component A sub phi, the angular component of the gauge field along the contractible cycle, on that state must vanish. So that's simply the condition that that the origin is a regular point, and that you are actually you do an integral on your manifold of a one form, not just of a connection. So okay, but this condition actually is very interesting and very easy to solve, because we work in a basis where AZ bar is diagonalized, where AZ bar is the coordinate, while AZ is simply the conjugate momentum, right? It's the functional derivative. This means that actually the equation that says that the gauge field along the contractible cycle vanishes at the origin becomes a linear equation, a first order differential equation, if you will, which is solved by very explicitly by this formula that says that the initial state, the state psi zero, is a squeezed state of your gauge field. It's just given by this expression, that's explicit and quadratic, and as promised, does not depend explicitly on the components of the vector, or the tangent vector to the horizontal trajectory, but only on the ratio. So it's unambiguous, even though the V's are ambiguous.
Sorry, Massimo.
Yes.
So you are imposing this angular component of the vector to be zero, the gauge gauge field to be zero, just at the origin. I see, but it could be pure gauge. So it has to be pure gauge away from it, right?
Now it has to be pure gauge, but when you do the functional integral, when you write the functional integral as the with an action that is ADA, you are actually implicitly saying that A is a one form, right? It's not just a gauge connection, it's a one form. If you want to, because otherwise this ADA won't make sense, right? So it means that actually your gauge field must be such that there exists a gauge in which the gauge field itself, the component phi, is equal to zero.
Okay.
So, and indeed, I mean, in some literature in Chern-Simons, you also notice that actually people say, this is an integral over one form. And in some cases, no, it's assumed that. Now, you can always do that for this particular case, but I mean, you can find gauges where this happens. So we just skip the intermediate state and we say we have a one form, and this one form is regular at the origin. Now, okay. on the other hand, this is maybe regular. This state is nice because then the gauge field along the horizontal trajectory vanishes, but it's not gauge invariant. It doesn't obey Gauss's law. This object is too simple. But radial evolution actually does the job for us, because when you evolve in time, and actually in radial time, you evolve for any amount of radial time, what you discover is that the evolution in radial time is actually a projection over the gauge invariant Hilbert space. So it is actually a radial. You can obtain this identity. It's not difficult to obtain this identity that shows that the radial evolution is actually the same as integrating over all the gauge transformations, large and small.
Okay.
So integrating over the small gauge transformations and then summing over the large one. So this is a non-trivial, but it's something that you can derive for the Abelian case. And so here we have in this case, we have exactly what happens even in gravity, right? When in gravity, when you compute the functional integral, this automatically solves Wheeler-DeWitt. Here we have a simpler version of this story. So radial evolution projects over gauge invariant states, and we can therefore use our non-gauge invariant initial state as a seed that generates the wave function corresponding to the vacuum partition function. So you start with a seed that obeys the right boundary conditions, that says that actually the gauge field is not singular, and then do radial evolution that will project over a state that obeys the Gauss law. And the integral over the gauge orbits, actually, that's the nice surprise, can be done explicitly, because after all, for Abelian gauge transformations, this integral is quadratic. So what I wrote here implicitly in terms of this function u can also be written explicitly in terms of the explicit form of psi 0 that I wrote before. Remember this v bar over v. And in terms of the form for the gauge transformation that I gave a few slides ago. Now, the integral is made of two parts. There is an integral over the lambda, that are the transformations connected to the identity, and also the large gauge transformations theta. So the non-trivial part of this Gaussian integral is actually the equation for the saddle point. Right? So I mean, you have this integral. Okay, fine, it's Gaussian, but you have to solve the equation. You know what is a Gaussian integral, but the Gaussian integral is it depends on the non-trivial dependence comes from the saddle point. Right? Now the saddle point seems to depend on the metric, this famous metric that was induced by this treble differential, and also on the choice of the vector v. And these are rather unpleasant things, because in the partition function, we don't want any of such auxiliary objects. We would like to have a partition function that depends on the boundary value of the gauge field, not on all this intermediate data. But in any case, let's proceed and see what happens when we actually do the Gaussian integral. So to do the Gaussian integral, of course, first you have to find the saddle point. Yes?
I have a question. So when you say that we get the gauge invariant states, is it by path integral over the radial component of the gauge field form? The way we get in like Yang-Mills theory, let's say.
You mean if it's an integral of AR, of the radial component? Yes.
Is it like AR times the AR times the generator of gauge transformations, and we are doing the path integral?
That's the reason why you end up with this identity.
Right. Okay.
Because the component. Yeah.
Okay. So Hamiltonian here is in some sense the generator of gauge transformations, is it? In this.
The Hamiltonian. So in this radial evolution, yes, in a sense, this well, I mean, Yes, you can think of it. I mean, because after all, you do end up with the same construction. Right? Now, the one thing that is not exactly identical, of course, is that if the Hamiltonian was exactly the generator of the gauge transformations, then here in this exponential, you would see the generator times the gauge parameter, and you would have to integrate over the gauge parameter. While here instead you have just R, right, which is actually a parameter that doesn't even matter. Doesn't even enter on the other side. But the basic reason why doing the functional integral. So basically, you do the functional integral in one way. You think of the functional integral as just an evolution with a Hamiltonian. And on the other, you simply do the functional integral. And as you pointed out, when you have the integral over the radial component of the gauge field that multiplies the generator of the gauge transformation, so you get that the same functional integral also is a projection over gauge invariant over the gauge invariant wave function.
Yeah. So and here we don't have a Wilson loop at the center of torus, right?
Not yet. We don't yet have them. We will have them at some soon, but right now there is nothing inside the handlebody.
Okay. Thank you.
So one question, Massimo. This construction has made the state, the wave function, gauge invariant, or it now transforms in the way that you want it to transform?
By gauge invariant, I mean that it obeys the Gauss law, so it transforms that it should under gauge transformation. So yeah, it obeys the Gauss law. Now, when I have this quadratic, right, I can just write the saddle point equations that have this form. Remember, A bar is the boundary value of the gauge field, of the anti-holomorphic component. Now, this A bar can be decomposed into an exact part, theta bar, an exact part, d bar chi, and the harmonic part, theta bar. And now you can substitute back in here and do a few manipulations of the equations of motion to arrive at another one that says that can be cast in this way. You have a derivative of all the exact parts. Lambda is a small gauge transformation, a gauge transformation that can be connected to the identity. Chi is the exact part of the gauge field, right? Because the bar of chi is a term in A bar. And here you have the sum of the two, lambda and chi, and dh is the derivative along the trajectory determined by the vector v. So this is dh is a derivative along the tangent to a homology cycle. Plus you have these two terms in v and v bar that are instead harmonic. Now, the equations of motion tell me that the sum of these three pieces, the derivative along the homology cycle, and then plus this harmonic part, is a holomorphic function. The function only of the local coordinate z on the Riemann surface, on the leaf of my foliation. Now, when you take an integral of this equation along a contractible cycle, the exact part vanishes by construction because it's exact. And what you are left with is an integral of these two harmonic pieces along a homology cycle, which has to be equal to the integral of a holomorphic function along that cycle. And that actually, again, it's easy to see that it leads to the following equation. The derivative of this function, lambda plus chi, along the homology cycle is equal to the difference of the two harmonic parts. Again, the simple manipulations lead from this to this. Okay, so now we have an equation that expresses basically this object in terms of these fixed quantities. So this is our saddle point equation. And when you substitute back this expression into the action, you find a very pleasant surprise. The pleasant surprise is that all terms containing the harmonic part of the gauge connection do not depend on the metric or v. So all the dependence on the metric and v disappears from the action, and then the quadratic fluctuations around the standard point are evaluated very easily, and the final result is, well, a sum over the large gauge transformation. In that sum, there is a part that just is essentially Gribov copies, are just identical gauge copies, and you have to throw it away as you do even when you do the integral for, say, gravity, right? And the rest instead gives exactly a very nice answer. This one that you may recognize as the Bose-Nair wave function for mu equal to 0. So in this case, actually, the integral over the gauge transformations can be done exactly, and it resums to precisely one of the Bose-Nair wave functions. So here the question of that we asked before: what is the linear combination of Bose-Nair wave functions? What is the linear combination that corresponds to the partition function without Wilson loops? Is very simple. It's just one of those wave functions, the one with mu equal to 0. And so let's see. So this is actually the end of the story without Wilson loops. And now we are encouraged to continue and see what happens when we do introduce Wilson loops. When we do that, when we introduce Wilson loops, right, we have to define a little better the Wilson loop, because it's a very singular object. I mean, so to make it less singular, we do the following. We take the Wilson loop and we write it actually as an integral of a gauge field coupled to a current with components W and W bar. And this current is just a vector field, right, that carries the same current as the Wilson loop. But we just spread it out. Instead of having just a wire, we make it wider, right? And we spread it along the surface. Now, this W, we are not non-committal about what it is. Right? The only thing that it has to do is that it has to integrate to give exactly the same current as the Wilson loop. Let's call this W of sigma, and so Wilson loop on the surface sigma, and determined in terms of the vector field W. Now, this W is a vector field. Well, in the case, in the original case where here you had a Wilson loop, was a very singular vector field because it had a delta of the cross section, right? Of the, but it's still a vector field, so it has exact parts and harmonic parts, and the harmonic part of the vector field must obey some conditions to ensure that this object has exactly the same properties of a singular Wilson loop. So we want. Massimo, yes.
One question. So this W should be one form, right? So that the integrand is two form which you can integrate over to surface.
Yes. Yes. So
this W is the.
So this is a component expression, yes, of
okay. Okay.
W wedge A. Right.
Uh-huh.
So this is the holomorphic component, is the handlebody component. Yes.
Right. And also you see there is this arrow which says Wilson loop is taken to this object. Now, what is the relation of this object to the Wilson loop? You want to take some limit of this to get back, because this naively seems to depend on W.
This depends on W, yes. So this is what you do when you do a framing, right? When you do a framing, I mean, you do something very similar, because instead of a Wilson loop, when you expand the exponential and you have n products of the integral, you split them apart a little bit. So instead of doing that, we take this integral, and this integral you can think of as a singular current distribution, as a wire, right? And we make it into a regular current distribution.
Okay.
So
I see.
So this, you can think of this as a regularization, or as being close to doing a framing, but instead of doing the framing after expanding the exponential, you can say, okay, let's do regularization in the exponential itself.
Okay.
Again, here we use the fact that our life is a little easier when we have abelian fields.
Thanks.
Are you converting this Wilson line to a cylinder kind of? Is sigma a cylinder, thin cylinder?
Sigma is actually the Riemann surface.
Oh, it's
so
a whole.
It's the whole Riemann surface. So W is defined on the whole Riemann surface. It is also true for A. I mean, you could write A in this form as an integral in sigma of some W and W bar, except that the W will be a delta of some transverse coordinate. Right?
Yeah, yeah. Oh.
So we are doing this regularization, but now this regularization has to obey some conditions because this Wilson loop is invariant also under large gauge transformations. And to ensure that, yes.
Sorry, I think I had the same confusion. I actually was thinking that sigma is like a tube. You take the Wilson loop and you thicken it up so that the current distribution remains along just the Wilson loop, but it becomes a tube.
Oh, yes, it's a tube. So imagine that then but you can say that W is 0 outside the tube, and then it's defined everywhere.
Okay.
So then you can say, you can thicken it and make it into a ribbon on this two-dimensional surface, but then outside, then W is equal to 0, and then at this point you can define W everywhere.
Okay. Okay.
So then is the charge mu will be the integral of this one form W on this?
It will be the integral of this form W on probably instead of integrating over the surface, exactly like here, right, where you have to cut this loop, which means that you are computing.
I mean, W is like current, right? So is the integral of that giving the charge mu?
Exactly. So at each point you have a current, right? So at each point along the loop. So if you take, say, if you have a tube, and on this tube you have a line, which is your Wilson line, you can integrate over a horizontal trajectory, if you want, on a homology cycle, and that will intersect your Wilson loop at one point, and the intersection will be 1 times mu, right?
Oh, yeah.
In the same way here, if you take this W and you integrate it over a horizontal cycle of sigma, you should get mu.
Okay.
And in fact, part of these conditions are actually these conditions. The condition that I just told you about mu is one of those that appear here, and that simply say that the harmonic part of W prime cannot be arbitrary, has to obey this condition for the regularized Wilson loop to be invariant under large gauge transformation. So this object is invariant under small and large gauge transformations, and this should also be invariant under small and large gauge transformation. And that's the.
I have one more question. So this mu should contain the information about the representation in which the Wilson loop is, right?
Yes, which in the Abelian case is just a charge.
So in that case, W will also have the information?
Yes, it's encoded in this equation for the harmonic part of W. You see that there is this term proportional to mu.
Okay.
And there is also another integer n that has to appear because the point is that now we have spread the charge over the entire sigma, so we get some extra conditions for gauge invariance. Now, the Wilson loop by construction is gauge invariant, so it commutes with the integral over gauge orbits. I mean, you can apply the operator W to the projection of the initial seed wave function, right? Or you can first apply W to the seed wave function and then project. In any case, W is gauge invariant, and the two results are the same, right? So we can also compute what is this W applied to psi 0, but psi 0 was a squeeze state. W is essentially a translation of A. You see from here. Remember, AZ bar is a number, and AZ is the functional derivative with respect to AZ bar. So actually, it's pretty easy to find the result of what is W applied to the initial psi. It is the initial psi times this correction. A correction that is the exponential of a term linear in AZ bar, and then also some term independent of AZ bar. Now, if you use this new state, psi multiplied by this exponential as the initial seed, and then you project over gauge invariant states by integrating over all gauge transformations, small and large, you will get the partition functions with an insertion of a Wilson loop, and that again has the form of a Bose-Nair wave function multiplied by this interesting phase. You see that, well, you may say, this is a phase, let's discard it. I mean, a basis is a basis of wave functions. I mean, they can always multiply them by a phase, but actually it would be a pity because this phase has an interesting interpretation. And it's the following. If you can write the Wilson loop as a, just by using its explicit form as a product of two component Wilson loops times this phase here, this exponential. And here I've written the two W, the W sub mu and W sub n. Actually, I've written the harmonic part of these W's. The part that is not the harmonic part actually plus the exact. So you see that essentially you have decomposed what before a Wilson loop that before had this exact part over here into two Wilson loops with where the mu dependent harmonic parts, sorry, and the n dependent harmonic parts are two different loops. What does it mean? This? Well, this means the following: what I call W, the Wilson loop of W mu, is what you obtain by blowing up a Wilson loop along a non-contractible cycle, while the other one, W sigma Wn, is a blow up of a Wilson loop along a contractible cycle. So but the Wilson loop along the contractible cycle vanishes on the initial state. If you compute the total Wilson loop and you write it as a product of two pieces, Wilson loop along the non-contractible cycle times Wilson loop along the contractible cycle times a phase, you will get only the Wilson loop along the non-contractible cycle. Because this term over here, when you apply to the psi 0, gives you nothing, right? Gives you the identity. So when we dressed our original Wilson loop, when we fattened it to and spread the charge over the Riemann surface, we actually introduced some extra ambiguity, right? An ambiguity that is exactly this phase mu times n. And actually, a nice thing is that when this phase n is itself proportional to mu, so when n is this integer mu times an n prime, right? This is actually what is known as the framing anomaly. So we got a result that in a sense is a little bit more than the framing anomaly, and this due to the following fact. When I passed from the Wilson loop to this W, I also identified different configurations of Wilson loop. I also identified a Wilson loop made like this. There is one loop along a non-contractible cycle, and then an extra number, capital N, of loops along the contractible cycle. In terms of, if you think of the loops along the contractible cycle, you may say, oh, they shrink to zero and they just disappear, right? But you know that that cannot be the entire story, because if you had a for instance, mu of this little cycle. So if you take a Wilson loop along a non-contractible cycle, think about a torus. Maybe that's the simplest case, right? A torus is a cylinder where you identify top and bottom, and then you have
Massimo,
yes, yes.
sorry, just one comment. I mean, at least it would help me if you could draw a picture of how the Wilson loop is patterned to this W operator.
Okay, so let me, maybe I should stop sharing this, right, and instead sharing a whiteboard.
Actually, sorry, may I ask a question at this point, which is related, and you may also use the drawing to explain that?
Yes.
Yeah,
Yes.
My confusion is the following. You may have a handlebody which has some genus G, and
Yes.
the Wilson loop that operator that you're considering, that doesn't span all the handles or all the holes, so to speak. So what is the relation between the original Riemann surface times this R that makes the handlebody and the Wilson loop, which may or may not be, may or may not know about the entire part of the Riemann surface? What I mean is that in this diagram, for example, that you've just drawn, there's genus is 2, but you may have a Wilson loop which goes around only, say, one of the handles, right?
Yes.
So what is the? Yeah.
I have a Wilson loop that goes, and I also have Wilson loops that go around both handles.
Yeah. So where is the information? I didn't follow exactly where the information about which Wilson loop you're considering and the relation between the original.
The Wilson, the information came from the. Let me see. Maybe yeah, I should go back to. Maybe it came from the fact that this mu. It's actually a vector. As you remember that it said that mu belongs to z k to the g, right? So mu is actually a vector with g component, and each value of mu can be either 0, goes from 1 to k, 0 to k minus 1. So that's the information, essentially. See how many times you go around each loop. So if you want to think about this, so this would be, say, mu1 equal to 2, and I don't know, mu2 equal to 0, and this is, say, mu1 equals mu2 equal to 1, right?
Yeah, so this part is okay. So when you what Abhijit was asking, that when you go from here to W, that W
Yes.
knows about which part of the Riemann surface, the one that has only genus 1 or the genus 2 in the first picture?
No, it knows about everything because mu, as you remember, the harmonic part of this W depended on mu, on this vector, the vector of mu, and on n, which is also a vector of integers. So yes, it knows about that. Now I don't want to share back, but I will do it once I'm done with this. Right. I think
it will help, Debashish, if you just draw the charge, the spread out configuration for the first example, let's say.
Yeah, that was also your question, right?
Yeah.
Yeah.
So the spread out configuration has the same homology, is homologous as, say, let's take this one, right? I don't know where you have 2 loops.
I see. So you bring it to the surface and then fatten it.
And then I fatten it, but I fatten it in a way that is homologous to this singular configuration. So this would be mu equal to 2 or 0. Now W prime also depended on mu and 0, all right? Let me think that there is I notice a problem of this sharing is that when you share something, you also lose the you also lose the talk. But anyway, let me go back maybe to the formula.
Sorry, just
I will write down the formula for W prime, right?
Yeah.
W bar prime is equal to, no, let me write it and then you'll see that maybe it will clarify. This is just a basis of abelian differentials, right? Omega is a matrix. It's a G by G matrix. Mu is a G by G vector. N is a mu is a vector with G components. N is a vector with G components. This mu tells you how many times you cycle around which handle, right? So here I wrote mu equals to 2, 0, which means that you go around the first handle twice and around the second handle 0 times, right? I could also go around the second handle once, and then here I will have mu to 1, etc., right?
Yeah, I think it's clear now. So the omega refers to the entire Riemann surface with the genus 2G, 2 in this case. And
yes, exactly.
it's
so
mu,
it's mu
which selects. Yeah. Okay, and the W bar also, or the omega bar is so also tells you what is it.
This is omega bar is simply the anti-holomorphic one form. It's the abelian, the anti-holomorphic part of the abelian one form, right?
Again, on the entire genus 2 surface, right?
Exactly. So there are, for a genus 2 surface, omega has 2 components. Little omega, right? A capital omega, the object they wrote here is a matrix that is 2 by 2, and mu and n are vectors.
So it's mu which is really selecting which W prime you get.
Exactly. And then at this point, you may ask, what is n, right? What the heck is n? Well, n, of course, is the select how many times you go around the cycle that is still a homologous cycle for the Riemann surface, but is contractible in the handlebody.
Right, yeah, I understand. So in going along, say, this vertical loop, you make some small detour around some horizontal loop, some capital N number of times. And those do not, those only give some phase.
Yes, and now you see that if you, so in particular, if you go around, so you can also add these Wilson loops around contractible cycles. And okay, since they are contractible, you the only thing that they can do at most is to change your wave function by a phase, and indeed it's exactly what they do. Now, if you have say, suppose that you have, I don't know, mu equals to 2. It means that you're going twice around a non-contractible cycle. If you do a braiding, right? Braiding means that actually every time you go around a cycle, you do a full circle, right, around some axis. So you have some axis, and then you have a loop and you go once. Now, for mu equal to 2, you will have to do it twice, right? You have to go twice around this pole, right? So this is the same as adding 2 Wilson loops around the contractible cycle. That also explains this last equation that I wrote for you, this n equals mu n prime, right? So when n is actually a multiple of mu, what you are doing is just braiding. And then the phase is the framing anomaly. So
thank you.
So yeah, you see, all of this convinces, it's a good test that actually we are doing something reasonable, it's something that makes sense. Okay, so this is actually all that I wanted to say for the abelian case. Now, I don't know how much time I have. Let me be brief also, because in non-Abelian case, we only have results for the torus. For the torus, we just choose as initial boundary condition some value for a phi, which is equal to mu over k. Mu belongs to the Cartan subalgebra. And as final boundary condition, instead, let's say that instead of taking a generic gauge field, we take only the harmonic part of the gauge field. So we take an, sorry, I have to share again back. So let me stop sharing here, and I have to re-share over here, hoping that I can do that without without losing everything. So share screen. Okay. And okay, so good. Okay, so here we are with the non-Abelian Chern-Simons on the torus. I choose as initial condition where the angular component of the gauge field is not necessarily 0, it's mu over k. So here, in a sense, I want also to include the case where I may have a Wilson loop. I choose as final boundary condition not a generic AZ, but an AZ which is purely the harmonic part. Forget about the exact part. Let's set it to 0. That's not so interesting. And I choose also this harmonic part to belong to the Cartan subalgebra, just to be able to do some computation. Okay. And let's see what we can do. Now here, we want to compute a transition amplitude, again, between an initial state in which I choose the phi component of the gauge field, the component along the cycle that contracts in the handlebody, and I choose it to be equal to some element of the Cartan subalgebra, appropriately multiplied by this 2 pi over k. And the final state is a state where the anti-holomorphic component of the gauge field is equal to some complex element of the Cartan subalgebra, which I write here. Now, the nice thing is that this transition amplitude in radial quantization is given by a simple functional integral, basically because, again, as it was pointed out earlier, right, if you integrate over the radial component, you get a delta function that says that the gauge field on the leaf is flat. So we get this integral. And how do you compute this integral? Well, you have to decompose the gauge field on the two torus as a pure gauge part and some exact component. The delta tells you that f is equal to 0 on each leaf of the foliation. So the gauge field is essentially the gauge transformation of a constant gauge field that belongs to the Cartan subalgebra. And then the computation of this integral reduces as exactly to what we expect, to a chiral Vesnomino model. And the integral over G actually was done in 1991 by Perrot. That's the reference that I know. And it gives a Wildcat's character of the gauge algebra, which I call chi of mu 11k. So this is a known result, right? So we are deriving this result now and interpreting in terms of radial quantization. So I do a radial quantization, right, in between the state where I fix the component along the cycle phi of the gauge field and the final state where instead I fix the anti-holomorphic component of the gauge field, I get a nice result that is expressed in terms of geometric objects of the algebra, the Wildcat's character. Again, the link between the boundary and the bulk is given by this A here. Right? So you have a chiral WZW coupled to this harmonic connection A. Okay, so and A is fixed by essentially in terms of this mu and u. Now, we know what is the initial value for the gauge field corresponding to the vacuum partition function. A phi should vanish, so mu should be equal to 0. Now, what we want to do is to relate the different values of A phi two Wilson loops. So we want to connect the functional integral with the insertion of a Wilson loop to these Kurzweil characters that were computed in a purely two-dimensional theory. Because maybe one thing that I should point out is that when you do this integral, you are doing actually a two-dimensional integral. You are doing an integral on a chiral Versumino model. Right? So there seems to be no memory of the bulk in this integral. Well, there is, and it is in this mu and u. Yes?
This k here in the while character, is it classical level or is it the normalized one?
This one is actually the classical level, but this is the classical level, yeah, if I recall well. I don't want to say something wrong, but to me it seems
because I mean, I had read in this Seiberg's paper that this k actually becomes k plus h, the renormalized level, but I'm not sure.
No, I mean, let me see. I don't. Let's say that you have a good point. I mean, because after all, we see this renormalization happening in many places, right?
I mean, even the Versumino-Witten model, which is dual to this, has the level which is k plus n or something, right? It's not exactly k.
Yes, yeah, because you are in a non-Abelian case, and then you have a renormalization. Now, yeah, I'll have to think about it. To me, it seems that it's k, but I should think better about that. And, let's see. Because when we compute the well, okay, let me show one thing that would seem to suggest that this is k, but when you compute the Wilson loop, right, then the Wilson loop can be written in terms of the so it's the trace over a certain representation of your gauge algebra of the exponent of the exponent of the integral of a, right? But you can throw away the exact part of your gauge field and only be left with the harmonic part of the gauge field, the component a sub t. You start from the vacuum where mu is equal to 0, right? When a phi has an eigenstate 0, eigenvalue 0. You act with the Wilson loop, and the Wilson loop actually you can think of it as being on the Riemann surface on the torus. You have phi, and then the other coordinate that you can call p. The gauge fields along phi and t obey canonical commutation relations, so they commute to some delta j times this 2 pi over k, and k here is the level, right? It's not the renormalized level, but actually, essentially, whatever is in here is also the same k that appears everywhere else. So maybe that can fix that can answer our question. And then, well, when you compute the trace of the exponent of a applied to this mu, you get a well, you know exactly what to get because this a has canonical commutation relation with a phi. The initial state is an eigenstate of a phi, and now when you apply this trace, you end up with a sum of eigenvalues of a phi, right? Of eigenstates of a phi with eigenvalues that belong to a root system of the representation mu. So you apply this trace, right, of exponent of AT. AT, remember, is a matrix that belongs to the Cartan subalgebra, right? So when you compute the trace of the exponential, you end up with this sum over the root of the representation. Again, taking this new initial state applying radial evolution, you get you get wildcat characters, right? Because for each mu, right, you know that the partition function, that the kernel, right, was given by a wildcat character as here, right? You know what is this kernel for each mu. Now, instead of a single mu, we have a sum over the root system of the representation that we labeled with mu. Then we end up with some exponent, and which is sort of universal, and it doesn't know about what happens in the bulk, correct? And then this sum of wildcat characters that instead depend on the initial state. So this is where the memory of the bulk is located. So this particular sum is the partition function in the presence for when you do a functional integral with this particular Wilson loop. Wilson loop that goes along the direction, along the non-contractible cycle of the torus and belongs to the representation labeled by mu. Let's say that mu is the highest root, for instance. Okay, so on the other hand, you have also an interesting story because the Wilson loop fixes the holonomy along the contractible cycle. One other way of getting mu is to say, well, if you take a contractible cycle, say this the cycle labeled by the coordinate phi, right? And you compute the holonomy of the gauge field A phi, when it goes around the Wilson loop, well, it will give you mu, right, by construction. So you actually have that for the two expressions for the functional integral to agree, you have this identity that it has to hold. And we don't know how to prove that it holds in general. It does hold for G equal SU2. And we proved this just by brute force. Now, the identity, the partition function that I wrote depend on the Katz-Weil character. But the Katz-Weil characters are determined uniquely in terms of the Weil character. So what we really need is an identity of Weil character. That is what I wrote here.
Sorry, Massimo,
yes.
These guys are functions of the complex structure also, right, tau?
So these chi are the Weil character. So I have this expression depends on the complex structure, on U and tau, yeah. Right?
Yeah. So I thought the next guy that you got for this other guy, mu, that was at -1/tau. I mean, I was hoping that this should just be an S matrix relation.
I hope so. I mean, we couldn't find. I mean, we were thinking about say a duality, right, between T and phi, so doing some soft type duality, but we couldn't find it. But I think it's an interesting question. I mean, how to prove this identity? We thought that it was that mathematicians would know it because it's an identity among Weil characters, but we couldn't find it. So we just in our paper we proved it just by brute force. Not
but
very
this chi mu is not at is not computed at -1/tau.
This chi mu is the Weil character, right? Not the Weil cat. So it depends on U. It depends on U, but not on tau.
No, sorry, but the initial equality that you should have before reducing it to the Weil character only is among Weil Katz characters, right?
It's among Weil Katz, yes.
So at that level, I would have thought that the right hand side is at -1/tau or something. Maybe I'm mistaken.
I mean, I understand. Maybe you say, okay, what we did was to say that notice that this relation holds when the relation among the Weil characters holds. But it's true that by doing this, we have lost something because we have lost the tau dependence. So it's true that maybe we should keep the tau dependence. Now, tau that goes into -1/tau is a duality, right? An interchange of phi and t. we couldn't find just for what we could see, we couldn't find a use of that duality. I mean, we couldn't use, we couldn't, but maybe we simply missed the point. I mean, it's not, we just tried a little bit to use this tau into -1 over tau relationship in the wildcat characters, and we didn't get anything, so we gave up. But there could be something there, right? It couldn't be that you can only prove this equality by brute force for, say, SU2 or for whatever group you can manage to compute explicitly. Yeah. So yeah, so this really is an interesting problem that we still would like to see solved, and it's actually the last thing that I wanted to mention. So now just back to the summary. The path integral of Abelian Chern-Simons theories on handlebodies can be computed explicitly by radial quantization, and the radial quantization from an initial state projects over gauge invariant wave functions. The initial wave function itself is fixed by requiring that the gauge field along contractible holonomy cycles is determined by the Wilson loop in general when Wilson loops are present. And the partition functions of non-Abelian Chern-Simons theories on torus handlebodies can be computed by methods similar to those used in the Abelian case. For non-Abelian Chern-Simons on torus handlebodies, we found that the validity of the radial quantization method requires an identity among Weil characters that we could only prove for SU2. And that's all that I have to say now. So thank you for your attention.
Thank you very much, Massimo, for a wonderful talk. Let's all mute and applaud. So we have had many questions during the talk, but if there are more questions, please go ahead.
Can you explain the last equality between Weil characters and Weil-Kac characters? How did you get it?
This one?
Yeah. This
one, I will have to leave this and go to the paper, right? Because it was just an explicit computation. It's not anything particularly.
No, I mean from not like computation wise. You said that you get this by equality between two formulas.
That's why this equality should hold.
Yeah.
So we the initial state that we chose was an eigenstate of A sub phi of the component of the gauge field along the phi direction of the torus. Let's say the torus has the phi and t direction, right? And they are both periodic. Phi is the contractible cycle in the bulk, in the three-dimensional torus handlebody, and t is the non-contractible cycle. The Wilson loop along the t direction, along the non-contractible cycle, up to terms that are exact, is the exponent of AT, where A is an element of the Cartan subalgebra. Right? And it's applied to an eigenstate of A sub phi. Now, A sub t and A sub phi actually are canonically conjugate variables. So when you apply this trace over a representation with, say, highest weight mu of this exponent, you are getting essentially the exponent of this A. A is like the conjugate momentum. It translates the A phi. So you start from equal to 0, and you translate by an amount equal to any of the roots that are in your representation mu.
You mean the weights of this representation, right?
Of the weights of the representation, yes.
Oh, okay.
Maybe I should say that. So yeah, I mean, let's take SU2, spinor representation of SU2. Then this exponent will be actually, we have an A to the multiplied by a diagonal matrix that is, say, 1/2 and -1/2, and that will start with the vacuum and then shift it to +1/2 or -1/2. Yeah.
Oh, okay.
This is kind of like Fourier transform, right?
Yeah, that's like a Fourier transform. But on the other hand, if in a sense, if you put the Wilson loop inside at the center of your handlebody, and then you compute A sub phi around that cycle, then that's exactly equal to mu. I mean, to this, the value of the Wilson loop. So you have an identity, you have the sum of our characters that should be equal to one character. And again, that's non-trivial. It happens to hold for SU2, but it would be strange if it was just an accident for SU2. But I think it's an interesting question.
I have one question, Massimo. It's a bit tangential, but does this approach give any insights about the Hilbert space when you cut a cylinder across, so that you look at the edge modes?
So if you take you take a cylinder, and then instead of cutting, you want
instead of slicing it in the radial way that you are slicing, if I cut it across, so that you expose the Chern-Simons theory with a disk.
Oh, yeah.
So you talk about the edge modes.
I think it has something to say. This approach has something to say about the edge modes, but I don't know what. Actually, our original idea, and I will give you actually a tangential answer to my to your question. And so let me do this. So our original idea was the following: was to say, well, let's take this handlebody and again foliate it, but let's try to. So the original idea was actually to say, well, let's do something different. Let's cut, say, your handlebody and then reduce the handlebody to say a set of spheres with 3 handles, right, and then cylinder. And then let's glue them together. So let's try to compute the partition functions on these cylinders and on spheres with 3 handles and glue together this partition function. Well, if you just consider, say, this cylinder, and you say, well, this is also a sphere with 2 handles. So what you are doing is that you are taking the gauge fields in the regions that I shade here, identify them with the gauge field that I shade here, right? And then integrate over them. We do not get the right result. So we knew that we were missing precisely edge mode. So again, another question that is open that at some point maybe we want to come back to is to how to take into account this edge mode. Because I mean, we ended up with radial quantization in a sense out of despair because we didn't know how to compute, to take into account the edge modes, and we didn't. So we said, let's try to have a way of computing it that does not involve them. But yeah, at some point it may be very useful to come back to this question and try to understand your question.
Thank you. Okay. If there are no further questions, let's thank Massimo again for a wonderful talk.
Thank you. Thank you. And have a nice day. For me, it's the evening, but for you, it's just the beginning.
Yes, yes.
Thank you very much
for keeping you so long.
Sorry for